Okay. Okay. So first of all, we start from here. All right. So suppose the output that I'm getting are, okay, for some reason this stops working whenever I'm connected to Zoom meeting. Otherwise, it works properly. Okay. So you have a node here. Let's just work with two nodes. And I wanted the output, this output is, let's say, y1, okay, and this output is y2. But okay, this is very, very bad. Okay, and you wanted the output to be y1 prime here, and you wanted this output to be y2 prime. So always remember, we assume that we have already calculated the feed forward. So feed forward is basically plugging in the values. So I have one example here. So there will be some input layer. I just pass those values forward, and I calculate value of each node, and I store that as vectors or as column vectors. And we have these values, what the outputs are coming, and we have we already know what we wanted. So this is supervised learning. So we know that we wanted y1 prime and y2 prime. So assume that our cost function is 1/2 of summation of yi minus yi prime whole square. So this is what the cost is for one example. Cost for one example. Okay, let me just write this way. So the derivative of this thing. So we just want to find out, if you remember from here, we just want to find out dc by d by 1. So dc by d by 1, from here, it's very easy to see. So this 1/2, why is there? It's basically just to get rid of the 2 that we multiply. So of course, we can multiply the cost function with any constant we want, because we want to minimize the cost function. So even if we take a multiple of it, if we minimize that multiple, that constant multiple, then the cost function will also minimize, will be minimum at that point. So it's just for convenience of finding derivative. So you take the derivative of this thing with respect to y1. So there are two terms here, y1 minus y1 prime, y2 minus y2 prime. So of course, while calculating derivative, you don't plug in the values, the actual value of y1, y2, you just take the derivative. So this derivative would be dc by, let me call it dc, dc by dy1, and that would come out to be this 2 we canceled, and there are two terms, one of them will just vanish because of partial derivative, and you will simply get yi minus yi prime. So this is for dc by dyi. So for yi, you're just going to get this, okay? So I hope this is very easy to see. Now, how do you calculate this value? This is very easy, of course. So you store another layer. So first of all, when we feed forward it, we create one list in Python, let's say. So let me just take a very quick survey from few of you. How many of you are familiar with Python? So we'll be doing some Python maybe. So how many of you are familiar with it? So is there anyone who is not familiar with Python?
Yeah, that's the better way to ask.
Okay, so I'm assuming that everyone knows this language. It's we just want some basic syntax. That's it. Yeah. So we'll store.
I have a question here, Hitar. Okay. Now I know that you're showing the mean square function in this fashion. Yeah. Now, the one question that I had was if say your activation function is a ReLU function. Okay.
Yeah. Yeah.
ReLU will be like if the weighted sum of that value is 0, I mean negative, then it will be 0, else it is the same thing. So the effect of the entire this mean square function will also have like nested if then else's, where the atoms are all polynomial expressions like this. So what I'm saying is, depending upon the intermediate value that you get as output of each of these nodes, your total, your overall function is kind of a piecewise polynomial. Okay, it's several polynomials embedded inside your the ReLU function, which is like and if then else. Correct? So when you do this differentiation, you do do it separately for each of those, if I may call it embedded polynomials? Because, depending upon the value, it's different polynomial, right? When you...
So, I mean, first of all, my question would be like, there's like, we are using ReLU, of course, but inside these layers, the equation function would just be, let's say, ReLU or sigmoid function. And there's nothing more to it. We cannot do too much with it. That is it. So these derivative, the functions that we are calculating, we can just, as I said earlier, we can just calculate them for once, and then we just reapply them all over all the neurons. And I mean, it will get clear. Just bear with me for 5 minutes, and I
So let's
think
go ahead. I mean, maybe it'll give you
yeah.
clear.
So there is no minuses. I mean, it's just some with this. So this is just yi minus yi prime. So this is the expected value. This is the predicted whatever the output that the network gave, and we just subtract them, and we get this. Okay, so this is what dc by dy I is. So you calculate this thing. Now, remember, this was the output of the neuron, and now we just have to go backwards, right? But as I told you that we need to uh, split the neuron in two parts. So one is before you apply the activation function and after it. So sigma, you apply the sigma and then this value is passed. So this is sigma of whatever value before it, this neuron passed it. And this is the value z, which is, which is the weighted sum of all the things coming from the earlier neurons, right? Now, forget for a moment, forget this part. So we just calculated this thing, and now we need to calculate the derivative with respect to this, and what it would be. It's very simple. Let me just draw it again. I think I already told all that, but let me just write it here. So you just see. So you just calculate this thing. You are calculating d of this. Let's name it z prime. Okay, z prime. So you're calculating dc prime by dc, and that would be sigma prime z. And to calculate the overall derivative of this thing, right? dc prime with respect to, not dc prime, this output, right? This cost. So there is a, after this, you calculate the cost. So to calculate dc by dz, you just multiply these two things, right? So the value of this is z prime, and you multiply that by sigma prime c. And yeah, you multiply, sorry, not the value, the derivative of this thing. I mean, okay, so the derivative of this is, I think I calculated it earlier. Yeah, this thing, sorry, this thing. So you multiply this with your this derivative, and you get the total derivative of dc by dz. So this is just one. Okay, so Pratik joined in. All right. So this is just one way, one step backward. So you just do this, and you get dc by dz is equal to yi minus yi prime, and you multiply that with this thing, sigma prime c. Of course, you can just remember that we already know these values. All of these values are stored when we were doing the feed forward. And this is just the label that we want. So you can calculate this thing and you will get this derivative. And now all you have to do is just apply the same thing and go backwards, right? But there's just one little thing that should be remembered. So is this also, if I want to calculate this, let's say for this neuron, right? There's one neuron here, so you can go back. Yeah, this neuron. So do I just need to multiply these two things? Will that be enough to calculate the derivative of cost with respect to these two? So just consider this is dc by dy1. So yeah, if I multiply these two things, will that give me dc by dz1? Okay, so
No, I mean,
actually no.
Yeah, you'll have
Yeah.
contributions from Z2, Z3, and so on, right?
Y2, Y3.
All right.
Right, Y2, Y3. So you just have to add them up, and you go backward from all of them. So I mean, basically, how you are going to store this. So you already have these derivatives, you store them in some vector. Let's call that delta for all the partial derivatives. You have the values, and then you just need to multiply them and figure out what to do with that. And there are weights here. So let's just try to find out. So what was the matrix here? If you remember the matrix, then we store in single row, we store the weights, this weight, and then this weight, and then this weight. So if this is W11, then this would be W21, and this would be W31, right? So it's actually the column that we are interested in, W11, W21, and then you have W31. So that's these are the weights, but they will be on the matrix M of the weights that you have. Let's call this the matrix M2, and that is called this M1. So the matrix M2, you are interested in this thing. So you take the transpose of this matrix, and you get this thing, W11, W21, W31, and so on. And why are we doing this? Because we need to add, to calculate this derivative, you need to multiply the derivative that you calculated here for each of this. So you need to multiply it for all these weights, right? So if I want to calculate this thing here, so I will multiply. Why are we multiplying, by the way? Can anybody answer that? Okay, just see what y1 is. So we're trying to find out this y1, right? So y1 is basically you take the weighted sum, and then you will take the weighted sum over all these neurons, right? So let's just focus on this way. So W11 times whatever the value this one was forwarding. So it is, let's call this value Z1. And then this W12 times Z2, and so on. So now when you take the partial derivative with respect to Z1, all of them will become 0, and you will be only left with W11. So along this edge, the derivative would be W11. And then you take derivative along this edge, the same derivative actually, dy2 by d. So you will find out dy2 by dz1. And here you will get W21, because we are only interested in this component. So for this neuron, it would be okay, so this would be the second row, that is W12, W22, and so on. And so you will take that value. So W212 and W22. So I hope it's like, it gets messy actually when you try to, but if you are getting the idea behind that, you understand that all you got to do is you need to multiply the transpose of this thing, M to T, with what? So what will you multiply this thing? So if you want to sum up all this thing, and you want to get all these things in one sweep, you want to get the derivatives, dy1 by dz1, dy by, not dy1 actually, you want to calculate dc. You want to calculate dc by dc1 and all of them. So that's why you're multiplying. And to get it in one sweep, you just take the transpose of the weight matrix, and then you multiply it with the derivative that you actually had. And those derivative were, you already stored that in the delta, let's call it delta L. So you already stored in delta L. So you just multiply it with delta L. And yeah, so that would give you just one single column vector, I hope. And that will contain some of the things, but there's one thing which is still left, and that's the activation function. So you also need to multiply by sigma prime of something. So I mean, you should work it out by yourself. I mean, it's getting messy and I cannot write even. So I hope this is getting clear. So it is like clear what we are trying to do is just chain rule, and you just have to understand that when you reach this node, okay, when you reach this node, you just have to assume that there is another node for W1. And to calculate this thing, you just have to find dz1 prime by dw1. And what is z1 prime? So we already know z1 prime is equal to this weight times, like this weight is as an input. So C1 prime is the weighted sum, right? So you have x1 times w1 plus x2 times w2 and so on. And so when you are differentiating with w1, you will just get x1, right? So this is, yeah, this is what you should get. Okay, so this way you calculate all the value and then you multiply all them together and you find out, you take the sum, and all of this can be written as one matrix equation using this column vector. So, I mean, it actually, I was not hoping that we'll get this messy, but if there is any I think this calculation everyone can do by themselves. It's just hard to write it all.
There's
This, so.
one thing that is, this is Srivastava. So
Yeah.
but your cat, okay, so there is a current weight, and what eventually through this calculation, what you're getting is the delta by which each of those weights have to be changed by.
Yeah.
Correct?
Yes.
Correct.
Yes.
Okay, but the mean square error function, it's a square on these things. So if you plug in all these things, it will be a polynomial. It's a second order polynomial. So the theta square will be there.
No,
So,
actually, we are not plugging in. So we are calculating the values. So why do you think we need to plug in anything? Like,
no. But
just,
mean error square function is a polynomial, second degree polynomial. Correct. So all the theta will be multiplied. Eventually will be that square.
I think there's one simple thing. So when you differentiate it, just see this. When you differentiate, you get this thing, right? This is linear. This is not a binomial. You just, because the square, if you multiply, differentiate x squared, becomes 2x.
You get the, 2x. Okay, so that's what, so all the expressions are, when you differentiate, are linear. Okay, so yes. So when you have x squared, it becomes linear. Okay, yes, because it's only a secondary polynomial, so all the expressions in the internal nodes, which are the result of differentiation, will all be in the form of linear functions. So that's why, and that is what you're calculating in each thing. Okay.
Actually, just to add to that, even if they were not linear, it doesn't matter to us. Even if this was some very confused, some cube and something, I don't know what, you just calculate this value and you save that. And after that, you don't worry about this function, because once you have calculated this value, so remember, that's why I said that first you do the feed forward.
Okay? Yeah, you're right. Once you've calculated it, is fine, even if it's not. But the way that you were describing was such that it is what you're propagating is all linear. Okay, so yeah, but in this case they happen to be linear, but in the arbitrary case it may not be. If the result of differentiation itself was a higher degree polynomial, then when you propagate it backwards, what you're evaluating may not be a linear function.
So again, I think this is, maybe I was not going to make it clear. So when you are doing this reverse differentiation, for each node you are calculating the value. So just look at the sigmoid function. So you have this derivative of sigma prime c, and which is the derivative of sigmoid function. Of course, it's not linear. It is highly nonlinear. It's like sigma of c times 1 minus sigma c. And sigma itself is 1 by 1 plus or 1 minus e to the minus x or something of this sort. And if you see this function, of course, not linear, but still it goes through, because you just calculate the value, you save that value. After that, you don't even care how you got that value, because you just need to multiply the derivative for this, and whatever the arrows are coming, you just add them up. So it's just numbers. So we're just dealing with numbers. So we don't have to worry too much about what the function was and how complicated it was. Once you calculate its value, you just save that value, let's say 3, and here's 0.3, and then you just go to this node and you differentiate these two nodes with respect to this node, and then you add them up. You multiply it and you add them up. That's the basic idea. So again, I'm really sorry that I made this very messy, but I hope the idea is clear. So to calculate this thing, you take the transpose and you multiply by delta R, and then you also multiply by sigma prime of something. I mean, you can figure that out what exactly that something should be, but I think it's already very messy, and if I try to do that now, it will just be a waste of time. I mean, if there's any question till now, like what are we doing, so just ask. And how do you calculate dc by dw1? I mean, this is exactly what I was coming to. So you just differentiate this thing with respect to this, and that value is x, and then you multiply that value. That is it. So so you do this for each layer. So for if there's another layer here, you just assume there are nodes, new weight nodes here, and for every neuron here, there will be, let's say there are six here, six neurons here, so there will be six weight nodes, and then you do this procedure for all those nodes, and that's it. Then you just multiply it and figure out what the derivative, actual final derivative of C with respect to W is, and you just store all that in a matrix, right? So whatever this layer was, so if it was 6 by 3, I don't remember, it's a 3 by 6, sorry, I guess. If it's 3 by 6, then you create another matrix of size 3 by 6, and you store all those partial derivatives, in this matrix, and finally you just multiply that by the step size. In NumPy, you can just, whatever, NumP or NumPy, whatever you call it. So in NumPy, you can just multiply S with this matrix directly, whatever your step size is, and you subtract that with your weight matrix, and that's how you get your new weight matrix, right? And that is all to it. So I will try to write this up clearly and upload this on the slide. So I'm not able to write that on slide. So if I can type it and then I'll upload it, go to a slide and you will understand what
And
exactly is
also,
going on.
writing up would definitely help, but having a very, very simple example, okay? I mean,
Yeah,
this can get very hairy very quickly, okay? As you increase the number of nodes. But maybe you can just have one hidden layer with only one node, okay, two nodes.
Yeah, okay.
Something like that, and some simple thing where you will show the propagation. So that will make it clear. Yeah.
Yeah, sure. So for now, I just want to ask if there's any question till now, then just ask. So and we can just like quickly
I
go
have a
through the
general
example and
question
all the
about the whole motivation of this process. So essentially, what we're doing is we're trying to take the mean square of the errors uh, as a function in terms of the weights and the biases, and at every step we are trying to reduce that function using the step, right?
by step you mean
I mean the
using the
step
step.
size.
Yeah, step size times the nabla of W matrix. So
Yeah.
you will multiply the particular derivatives. Yeah. So you just not subtract the of course you know that you cannot subtract just the step size. You have to
Yeah. I
multiply
mean
that with
the step size is proportional to Harvey.
gradient. Yeah, the
Yeah. Okay.
gradient. Yeah. And so all of this algorithm is basically a chain rule. And there's
Yeah.
one paper which I wanted to like show you, but I don't think I have that one right now open. So this was proposed by a psychologist. So it's pretty interesting that that a person working in cognitive science published this, which got so like which made this whole field develop crazily. So all right. So if there's any doubt about this process here, then just let me know. So I will just go through one simple example in 2 or 3 minutes, and then you can just proceed so that we can just end it. So is there any question for this process? Anyone?
Well, I just had a comment in response to the question that was just now raised about the step S, the value of S. That is actually embedded. Okay, that's a given. That's something that is given, and it is embedded in the error function. Correct. So what you're computing is the derivative of the error square function, in which that step is predetermined, and it's a constant, correct? So that is not varied for for a given backpropagation process. That step function is fixed. So every time.
So there's one little like
scale,
that I would like to add.
not a step
It's
function.
not added to cost function, so it's added to network. It's fixed in the network, but it's not like it's fixed in cost function. So you are using the cost function to calculate the gradient. Once you calculate the gradient, you just multiply that with the step size, and then you subtract it, right? So if there is any question regarding this, then let me know. Otherwise, I'll just proceed with one simple example, and then we can go ahead with other stuff. Okay, so I think there's. let me try to give you one simple example. So let's assume this is, I have a training example which is saying x1 is equal to, let's say 1, and x2 is equal to 2. So you create two nodes for this. Of course, we're not going to use these nodes because we don't want to differentiate between x1, x2. But for let's just write them as node. And assume there's just one neuron, and it's using ReLU. Sorry, it's using ReLU. And so these weights, let us fix some values for these weights. So this is the weight node. Remember, this will just become a competition graph. So let's say the weight was 0.1 for this, and so this was also going in this neuron. And there is another node which is W2, and let's call this was 0.1 as well, and then it's going in. So these are the four inputs. Of course, we won't be going back along these edges. They're just for demonstration. And now you just output it. Okay? Let's just use.
Let's see. So the W1 and W2 are the weights for the X1 and X2 edges, or there are additional edges here? I mean, you don't have weight. No, you showed W1 and W2, but you don't have any weights for the X1, the edge going from X1 and X2.
Okay, so this is not a DNN. I'm not drawing a DNN. I'm drawing the competition graph for that. So I'm just separating the nodes for W1, W2 separately, and I'm thinking that this will just multiply W1 by X1, W2 by X2,
okay.
and
So
then
W1,
take the weighted sum.
W1 is the weight for X1 to be multiplied. Okay.
True. So this value, let us call this node N1, and this value will be sigma of N1. And to make it like the backpropagation, okay, how it works. So let's just distribute that along 2. And let's say there's just one node for weight here and one node for weight here. Let's call these weight W3 and W4. And their value be 0.1 and 0.2. Like I just want the small numbers. And just call you apply the you are applying linear activation here. For the simplicity, I'm just not using ReLU now. And this is what the output is, and these are the output values. Okay, so we have all the weights, we have all the function. This is ReLU, remember, and we're just going forward. And this node is 0.2, 0.1, and you are outputting this value. Suppose I wanted on giving 1 and 2, I want the output to be 2 and 3. Okay, that is what my code was. And let's just, okay, I don't know how much time is left. Okay, we are already getting late. So,
I mean, if see, there's normally it's at you go till 4:45. We started 5 minutes late, so and with the disruption, it's 10 minutes. So you have another 15 minutes as long as it's okay. So I'm expecting that you have till 4:50, another 15 minutes. So is that okay?
Okay. So I think, yeah, I think it will be enough. So
yeah. So I want to make sure that it's okay with the audience. Okay. Yeah. So you have 15 minutes. Yeah. Please go ahead.
Okay. All right. So now this node, we name this N1. Let us name this node N2, and we can name this N3, and this is N4. So I'm really sorry about this.
So the 2 and 3 are the expected, not the actual.
Yeah, this is the expectation. Yeah, let me just put this in box. So this is the expectation which I want, the values that I want, and on input 1 and 2. So this training example is given, all the weights are given. I just want to, first of all, we do the feed forward, right? So let's just do that. Okay, so you start with 1, 2, you multiply 1 by 0.1, you get 0.1, and you multiply 2 by, let's make it 1, I guess, otherwise the output will be very bad. So you will get 2 plus 0.1, this is, so the value that you will get here would be 2.1. 2.5. Now you apply the ReLU function, of course, the same value will be forwarded, and you again get 2.1. Just okay, and now you, so what will be the value output here? Remember, this is a linear activation, so for the simplicity, so what is the output here? 2.1 times 0.2. Let's also make this one. Let's make it 1, and let's also make this 1. So I'm doing this because So the value is at least somewhat close to what we wanted. Otherwise, it will go really, really low. Okay. So this is 1 and this is also 1. Okay. So you multiply 2.1, your output would be 2.1. Okay. And if you multiply with 1 again, and then this output would also be 2.1. Okay. And now you want to calculate. So let us calculate the derivative for this node. So there's a linear equation, so we can just directly calculate this one. I want to write it, but I don't know if there is enough space here. Okay, so let's try it. This is it's not even selected. Okay, I think I can now write it. All right. So let's commit this node. You just have to calculate. Like this is just a linear equation, so nothing will change. Whatever the derivative we want. So let's just write this dc by dn3. So this value would be, if you remember that equation that I wrote last time. So the derivative is this, right? The difference. So you just write that. So dc by dn1. So it is 2.1 minus 2, which is 0.1. Okay, and for this one right here, so dc by dn4, it is 2.1 minus 3, which is minus 0.9, I guess. Yeah. Okay, now if we go backward. So once we store this, now you don't have to worry about the cost function. Remember this thing. So now you don't worry about cost function. You can just go backward. Let's just calculate this one also, because we need to go back this way. So what is the output of this thing? So this node n3, it is giving you what? What is the function that it's calculating? It is w3 times this n2. So w3 times times n2. And now if you differentiate, you find dn3 by dw3, then it would be just n2, right? So this value is simply n2. So until you can just write n2 here. And I will put the value for n2. N2 is 2.1, so that is 2.1. Okay, and what about this thing? So again, this would also be W1. So output of this neuron is W4 times 2.1, right? So this derivative will also be 2.1. So that's okay. Now we have so now you see. So what is dc by dw3? So let's just calculate this thing. What is dc by dw3? Anybody just please say it? What is dc by dw3?
What is
Shomudev, will you like to answer it? I don't know if he's even here.
Is that W3 or W?
It's W3. I mean, I have not reached W1 yet, so it's W3. We are doing much differentiation. It's very simple. You just multiply, right? You just multiply the two derivatives.
So 0.21.
Exactly, 0.21, right? You get 0.21 because we multiply 0.1 with this thing. So and maybe the calculation might go a bit wrong, but of course the idea should be conveyed. For this one, what is dc by dw4? This is w4. So what is dc by dw4? This will become just multiplication of 0.9 with this 2.1. I mean, of course. So this is how it's calculated. So now you go back this way. So like just do it for one more node and we'll end this. Otherwise, okay. Now just see this node. Now you store. Okay, this was very important. So you store this derivative, whatever you calculate till now. This is 0.1. and this is 0.9, and you are going backward here. So let's calculate it. Let's calculate for this edge. So this edge is saying, this edge is asking us to calculate dn3 by dn2, right? dn3 by dn2. So whenever you are at this node, a particular node, let's say its name is n2, and you are trying to find out for this edge, which is going from n2 to n3, then you find out dn3 by dn2. And what is the value of n3? This output, whatever the output is giving, what's the output of n3? It is just like this. It's just w3 times this value, whatever this output was.
2.1, huh?
Yeah, this m3 was w3 n2, so differentiating with respect to n2, so you get w3 as our answer. And we know the w3 was 1, so you just write 1 here. Similarly, we just need to find it out for one more, this part, and this is n4, n2. So you find out del n4 by del n2, so now I'm saying del. Okay, and that would be, again, this would be w4 times n2, and we differentiate with n2, you get w4. So it's w4, and w4, the value of w4 is also 1, so this will also become 1. And I think now it should be clear that what you're doing. Now you just go back once more. Now this is sigma, this is ReLU, and its derivative depends upon the value. So if it is positive, you just put 1. If it's negative, then you put 0, and that's it. So you come back here, and so you first of all calculate the derivative here, exact value. So what is the value here? You calculated the value for this node already. This was dc by dn3 was 0.1. So this is 3. So my 1 and 3 are part distribution. 0.1 times 1, and you get 0.1. And sorry, you get 0.1. And then you add along this edge. So this is 0.9 times, again, 1, I guess. Yeah, again, 1. And 0.9 times. So you see one more thing. Like we multiplied the weights. The derivatives came out to be weights. That's why we are multiplying the transpose the matrix there. So why transpose exactly, you will figure it out yourself. It's easy to understand. So this will be 0.9, and the overall you get 1 as the answer for this derivative. And now when you're going back, you have calculated this derivative of this node with respect to, like, you have calculated exactly dc by dn2. And now you don't care what you did in this area. It's just something which you don't even think about. You just go back, and now you just assume that you are applying sigma over something. So what is this? What is the value of this node with respect to this node? So we want to find out dn2 by dn1, and it would be sigma prime of n1. Because this is sigma n1, so you have sigma prime of n1. And what is sigma prime of n1? Depends on the value of n1. So what is n1? n1 is positive. So it means that the derivative, if you are using ReLU, then it should be 1, and you put a 1 there. Okay, let's just do it fast. And you do this for W2, and I mean, I hope you get the thing. It's just
if that was negative, then what would you do?
0. I'll put 0. If it's 0 or negative, then I'll put 0. That's it. And you see, this is one of the things that it's in ReLU, a neuron can in some sense die. So because the derivative is 0, so everything before it won't be changed. So none of these weights can be changed if the derivative becomes 0, for that training example. And therefore, this is called as I mean, if I'm getting correctly, dying ReLU problem or something. And the point is that if the derivative for all the examples becomes 0, and then you will never change this weight. So that neuron is just lying there calculating nothing, because it will always output 0. And so for that, we use something called as leaky ReLU. And the idea is simply that instead of having this graph, like this flat, you just say, okay, I will just make it like this. So you just add an alpha here. So you write alpha x. That's it. So this is leaky ReLU, and this angle is very small. Usually it's 0.001 or something of this sort, so that a neuron doesn't lose hope that, okay, maybe someday it will learn something. That's it. Okay, so now I hope it's clear how you're calculating all these derivatives. Now you want to calculate dn1 by dw1. It's just weighted sum. So it should be the value of this thing. So W2 times X2. So it should be 2 because this is how it's calculating. N1 is equal to, let me just write it for completeness, X2 times W2 plus X1 times W1. So when you differentiate with respect to W2, the answer is X2. So you just put 2 here. And now you just multiply 2 with this 1, and you get the derivative is 2, and you get a derivative here, and so on. The point is you only store the derivative at one particular layer, and then you just calculate all the derivative before that. I mean, just the layer just right before it, and that is what you are back propagating. That's it. So now, is there any question till now? I hope this example actually clears up everything, that how that propagation is working. And remember, you need to implement this thing. I mean, I'm asking, even no matter whether you take the course, try to implement this. It will be really fun, and don't, because the code is available online, don't actually see that and try to do that on your own using just numpy, and I'll give you the stub file and you can just play with it and figure out what to do, how to implement this. And I think everything will get clear when you do that. So is this example clear? Is there any question that, or did you finally get what is backprediction is doing? It's just chain rule in disguise. That is it. Because we have very little time left, so I'll just assume there's no question. Go ahead. Okay, so this is, I'm just trying to explain all this. Let's forget this thing. So you have to use the matrix approach, and you are not going to do it for like for each neuron one by one. You will just use matrix and multiply the transpose and whatever, and you can figure that out what you exactly need to do. I guess there. So let's just go to SGD, that is stochastic gradient descent, and this is one of the algorithms to implement that application. And the thing is this: so suppose I have the huge data set of, let's say, 10,000 training examples. And if I am calculating for each update, I'm using the whole 10,000 thing. And remember, you have to implement this algorithm for each example. So for each example, you fix these values, and then you do this whole reverse propagation. And there will be like thousands of nodes here. And you calculate one gradient for this one example. And then you take the average of that gradient over all the examples, right? And that's why—
samples, right? You mean samples?
What?
You
Yeah.
meant samples, not examples. Yeah.
So by example, I mean training examples, training samples, training data. Let's call that. That's right. Anyway, so we can understand that it will be really heavy on the computer for calculating all this. So what we do is you take the data set and you divide that into mini batches. Let's call them batch 1, batch 2, batch 3, ... And then you calculate the gradient for this batch, and then you update your network. And then you calculate for this batch, and then you again update. So theoretically, when we just study the simple SGD, we say that every batch is actually, we get the batch by randomly sampling, let's say, K numbers of training training data pairs, and then you just get them, and you implement this backpropagation for each of the example and sum them up, average them up, and subtract from your weights and biases. Okay, sorry, I forgot to add bias here. So of course you can understand that if you just add one node here and you add that's what bias is. And because the bias is just added in this value, and it's just 1. So whatever the derivative you calculate here, that is exactly the derivative of bias with respect to cost. So yeah, I mean, if I'm, okay, you can check that out if I said this correctly or not. So you apply the gradient descent on each batch and update the weights and biases. That's what SGD is. And in practice, you don't actually sample K number of training data points for on each iteration. What you do is you randomly shuffle the whole training data set, and then you just take these many examples, then these many examples, and these many examples, and go on. So this is, let's say, this is some way of picking out object without replacement. So this is why this works. Exactly this, the thing that we implement in practice. It's very hard, or I think I don't even know if somebody has written something on this, that why is this working properly when you don't replace, because it's mathematically really involved and difficult to argue about. But when you are using when you assume that you are just sampling all the examples in the mini batch randomly and with replacement, then it's easy to understand that it's just, you can just use this a law of large number that when you do this again and again, you will reach your optimum. So there's some expectation and all, like some simple math involved with this, but we won't be going into that. The point is that in practice, we actually shuffle the data set and then just use, in Python, you know this function. You use range 0 to n, let's say n is the number of examples, and you say mini batch size, something like this, mini size. And you take this thing, and then you, your example, whatever the example is, you just, I mean, for I in range, and then you take I to I plus size. I mean, this is the way you find these batches, and you just keep doing all this. And you already shuffle this, so it's without replacement. That's it. Completing the traversal of whole data set, this is called one epoch. So if I start from here and I complete everything, then this is what I think we call an epoch, and that is what at least we'll call an epoch. And that's it for the SGD. So we'll just see the code very quickly, and we will discuss that in detail in the next lecture. Then we will also have TensorFlow examples, and that would be, for the most part, that would be it for this neural networks. So let's just discuss overfitting, underfitting very quickly. So what's overfitting? So
Siddharth, in the,
yeah,
since we are overrunning, if this is,
yeah,
I don't know if you want to defer this for next class. So
I think I will like to ask if you guys can stay for 5 minutes. I think that is all it will take to cover this, because I will revise that again maybe in the next lecture, but I want to finish this because so that we can actually implement, we can get started with the implementation of our assignment.
So 5 minutes, is that okay, guys? Yeah.
Can somebody please speak?
Yeah, I'll assume it's okay. Yeah. Go ahead.
All right. Okay, so overfitting is basically that your model fits too well with your training data, and what happens is that the model learns the noise in the training data. So because you are just iterating epochs over the training data, what will happen eventually is that to get it cost near and near to like 0, let's say, it will just figure out what the noise pattern is in the training data, and will figure out somehow that, okay, this is the output for this way. In some way, you are saying that it memorizes everything. Yeah, it memorizes data instead of recognizing the pattern in the data that we actually wanted it to do. And that's why it leads to great performance in data. But when you test this on the testing data, you will find that it's pretty horrific. So just see this. So whenever you are applying gradient, you know that this cost will go down as you iterate more. This is the number of epochs. So as you iterate more, this cost will go down. I think I described that on the first lecture as well. And your testing data and the cost on that is also going down. But after a particular point, your testing data, the cost on testing data will increase, and your cost on your training data will keep decreasing. Of course, this will always decrease. Like, okay, not in SGD actually. In SGD, this can fluctuate like this. But anyway, so this will decrease. So we don't want to go beyond this point. So this is what you call as overfitting. And if you just don't iterate too much, like a sufficient number of time, then you are doing what is called as underfitting. So you are performing bad on both. You are performing bad on your training data, and you are performing bad on your testing data, both of them. So that is actually like both are worse actually. Even this is bad and this is bad. So we don't want any of this condition. We want to stay in some particular range, and that's why when I was discussing in the second lecture, I mentioned again and again that we don't want to reach the minimum. We just want to approach sufficiently close to the minimum. And okay, so that's it for the overfitting and underfitting. And for the last thing, we have regularization.
How do you decide that?
This is basically,
how is that decided? How do you decide where? Because so you first train using the data.
Yeah.
You don't have.
So you're calculating all this. You are calculating this cost, and you can see when this cost will start to increase, and then you stop. That's it. The iteration at which the testing cost start to increase, then you stop. Does that answer your question?
Does for all all training data, the graph look like that?
Again?
Does for all training data, the graph look like that, like it separates
like
and then, yeah.
I mean, of course, we cannot generalize this. This is what you see empirically. When you will do this on your, let's say, on computer, then I'll ask you an assignment to plot this graph and then see if this graph is like this or not on your data. So you increase the number of epoch, and every time you do this, you store the cost of this and cost of this, and then you plot them using matplotlib and see if this pattern is there or not. I mean, we hope that this is what you
Means
see.
during a training phase, you have to store some non-optimal things as well to see if it is good enough for the thing, right? Because with the training,
So
if you go all the way to the minimum, then that may not be, you'll never know. So unless you have saved some non-optimal ones at various points, you don't know how bad it performs on the testing data. Correct?
okay, so what happens is that you've given a data, you partition that into two parts, and this is training, this is testing. You train only on this, you test on this, and then you plot this graph. So if I give you 10,000, then you separate 1,000 for testing and you use 9,000 for training. And then you keep doing and plot this graph and see when it starts to like diverge, and then you stop. That's it. So let's just go. I mean, let's not do regularization. It's very easy, but let's not do it for now. I just want to show you. Let's recap. Like we discussed this, we are already late. I wanted to show you this code actually. Uh, okay, so this is just because so that you can implement that on your thing. So I will share this notebook with you. This code is available to you. So I have hidden this network code in this file, which I will not be giving to you. I will put the stub code here, and then you can fill all that up. And so let's see this thing. So here, there's something called MNIST, and MNIST is basically all the handwritten data, handwritten digits, and then so this is some function that you can figure out on your own that what they are doing. It basically like, uh, so basically what you're doing here is that you just reshape your images in the vector form. As I told you that you always have to flatten your input, at least when you are dealing with these normal feed-forward neural network. In conventional, uh, in those convolution networks, you might not actually do this. Anyway, so you can figure that out what all this is doing. So I'll just show you one thing. So if I could just run this for now. Let me start from here. So you have to, I hope you know how to install all this. So pip install mnist, that's the command that you will use for this. If you don't have notebook, then use Jupyter Notebook is available online. You can use that. Or even there's a collab.research.google or something of this sort, and you can search that and you will get the notebook for you. Otherwise, I'll say that I'll advise you to install Jupyter. Let's just wait for this to evaluate. And okay. So now we are training this thing. So this is what network is being trained, and you will output this epoch that, okay, in epoch number 1, you are getting 3,400 correctly out of 10,000. Then you are getting 4,000 correctly out of 10,000, and this will just go on for a while. And this is what we mean when we say it's learning kind of, and it won't reach to. So this is the learning rate. I'm sorry, and this is the I mean I'm not if I'm getting correctly. It was the batch size, that how many mini batch size, and this is the number of epochs. Remember, each epoch you traverse the whole data set. Uh, that's what you do. So I will actually give you good enough code for this, so that you don't have to like struggle too much implementing backprop. You just have to do some basic thing, and then you will get it. So you see, this is like this rate. It's actually increased from very quickly initially, but now this rate is decreasing. Of course, because of this graph that we saw, that as you approach this minimum, this rate actually of decrease, it's actually start decrease as well. Uh, so yeah, I think we are going to get all of them like in 29 epoch, 30 epochs. Then I'll show you this. For while it's learning that thing, we shall go to this part. I think there's not enough time to cover all this, so I'll do this next time. So this is exactly the example that I was discussing, this one. So I have written the code for this network, and I've written some utility function that can help you visualize this, that okay, this is a cap, this is a square, and we add a noise to it, so it's not that dummy example now. We add noise to all this matrix, and what you get ultimately is, let me just call this function. Yeah, so you get a noised version of the of this shape. So if you see this, there's some darker and there's some lighter. So you will get some noise in. So this will just add the noise to it. It's basically just adding the normal distribution and with 0 mean and 0.05 variance, and it will add to everything. I mean, if I give you, when I give you this notebook, I think you will realize everything, how it's working, and everything is there already. The code, how do you so let's just do, if I think it's done, this epoch is done. Okay, so it's learned this. You're seeing the rate is pretty good, like not really good, but it's okay. So this is how you use the model. So you just call feed forward function, and I pass the image to it, and this is the image. So this is the function to show the image, plt.imShow, and the label is 1, and the prediction is also 1. So that is good. Let us try to change this thing and see. So label is 4, prediction is also 4. The label is 6, the prediction is 2, of course. Like this is kind of like 6, I don't know. Of course, our network is pretty bad, doing pretty bad, but you can try to increase this. Like you can try to figure out ways to how you're going to decrease this error rate. So you will have to implement this. I will give you the stuff file, and I hope if there is any question regarding this algorithm that we're doing, then you can ask even later if you want. And secondly, this all code, you just have to run all this code. After you are done with your network, just write a file called nn networks, or like just put the code here. I will just put the stuff code here and just fill it up and just see if all of this works true or not. So all the functions will have their signature and description, and you just have to fill the code. And then this will also work, and this will tell you, okay, let's just run this for now and see. Okay, so I didn't actually run all them. Okay. Okay, so this is learning quite fast because I just have a few examples, and you see it's already 189 out of 200. And this is the matrix, and it predicted L shape. So that's cool. And if again I run this, so this is what is predicted, square, and it is actually kind of a square. So I think, I mean, you will like to do all this if you do.
What?
Okay, so if
You're running it on a different test data? What
yeah,
is
this is something which I just wrote. So example, I can just show you the change. I can just change it. So if I make it 0,
brief in your answer because it's getting late. So is this when you ran something earlier, you ran something now? What was changed from the first run and the second run? That was not very clear.
so these two ones. These two.
Was it the test data that changed, or you running it on a new network, or what?
So the network is same. I'm just running. I'm just asking. I'm giving it an example. I'm giving it a problem that, okay, classify this particular shape, and it's telling me that, okay, this is L shape. That's it.
After you trained it, you're
yeah, it's trained here. So this was the training part. It's already trained, and you just
Are we supposed to implement the computation graph?
Yeah, I think
no. You won't be like you won't be doing the competition.
Wait a minute.
Okay.
So I'm going to veto here. So because it's getting very late, okay? So what we will do is, this is what I'm proposing, that I don't think, even if you, Hitat, if you start describing what they're supposed to do, unless it is, since it's late, let's write, let's write up what they're supposed to do on a piece of paper as a document, okay? And then we will upload it on Moodle. And if they have any questions, then it will be clear, okay? Then they can ask, and then do it. So I suggest, would you agree that that would be a better thing to do rather than?
Yeah, anyway, I'm not going to explain all this right now. So you have to implement that. I'll give you the stuff code and everything.
And also, I think this portion, because of the time we had to rush through, and I'm not quite clear, okay, if they got all of what you said in this part. So it's better that we write it up, publish it, exactly what they're supposed to do. And if they have any questions, they can.
Yeah, sure. So just for the end. So we are done, or we are done with this, and we will pick it up again. So I will show you the right code if some of you cannot figure it out and explain all that.
Yeah. If
Next
there's a
time.
good way for you to answer his question, please go ahead. But
Yeah. So the answer is that no, you are not going to implement a competition graph like as a graph that you're storing all the nodes. You just use some list which has some column vectors in it, and that will store all these the values for this layer, values for this layer, and the derivatives for this layer, derivatives for this. So you will have two matrices, one for values, one for derivatives, and you will just update them as you go backward. And you will subtract it, and you do all this. The stub code will be will make it everything clear what you're supposed to do. So I'll fill up the lines. You just need to kind of fill in the blanks. So it will be really easy to do all this. Just don't look into online resources for that. That's the only request that I have.
If you were to describe in one sentence, they will be implementing the back propagation algorithm as you described, but not completely from scratch, but you will write up some code where there'll be some blanks which they have to fill in. Is that correct?
Yeah. Yes.
So but when they fill up all the blanks, they would have implemented all the steps of back propagation algorithm as you described.
Yeah.
Okay.
So if there's any question, just quickly you can ask. Otherwise, we have to end it because I'm sorry, we already are.
Okay. Thank you for
I just, Professor Srivas.
Yes, please.
Yeah. Can I just talk to you for 2 minutes after the class? This is Sahil.
So you can stay in this meeting, and everyone else.
You want that Sahil? You want that one-on-one? Is it?
Just a quick 2-minute chat, not related to today's lecture.
No, I understand, but does it have to be one-on-one?
Yes.
Okay. So then Hitarth and Madhukar, can we, first of all, is it, okay, the rest of you can leave the meeting.
Or what we can do is I can just maybe call you or email you. Maybe that's better.
Yeah, I'm planning a meeting with Hitarth and Madhukar immediately after this. Okay.
Oh, okay, I see.
So, but what we can do is you call immediately after I end this meeting, and Hitarth and Madhukar, if it's okay for you to have a meeting now. I mean, Hitarth may be tired, so then we can do it tomorrow also. But nonetheless, if it is okay, then we will do it half an hour from now with another meeting. And with another, Google meeting or something.
Okay. So why don't I just?
No. This is I meant for you immediately.
I see.
After this, okay.
Okay. So I propose one thing. So let us do the meeting. Let everyone can leave, including Sahil. And
everybody.
I will message Sahil that okay, when we end this meeting, I will text Sahil that okay, now you're free, and then he can maybe call you up. Okay.
People, yeah. So I think, okay, let's see. So I'm going to end this meeting, okay? So that people are still hanging around. So I will end this meeting. And Sahil, you can call me, okay? And Hitarth and Madhukar, we'll chat half an hour from now. Is it okay?
Yes, that is. Yeah, so that's okay. So roughly at 5:45.
Correct. Yes. 5:45.
Yeah, so I'll send a Google Meet invite at 5:45.
Okay,
Yeah. Okay, sir. Thanks.
I'll end this meeting.
Yeah.